Okay, so I've adjusted the due dates accordingly. As I mentioned when I came in, you can retry the two questions on sorted linked lists, the remove duplicates and sorted intersect for up to half the points that you missed. So if you got like, I think there was a total like close to 30 points on them, but if you say you missed 20 points, okay, then then you can get 10 back. So I'll make a formal announcement. Please try to have it done by next week. I'm not going to put a formal due date on it, but the sooner you get it done, the more benefit you'll get from it. Today, what we're going to do is other administrative things. So the next couple of honestly, this next few weeks will be mildly chaotic for me, meaning that you'll be having some classes over Zoom. So next week, why doesn't it just pop up with the calendar? Okay, here we go. Next week, on the 18th, I need to attend a funeral in D.C. It's at Arlington, and if you know anything about that, that means it's not a recent death. So anyway, 18th. So at the 18th, I'll be holding that via Zoom because I'll be taking a train into D.C. early in the morning. Then I think April 8th or so, 8th and possibly the 10th will also need to be over Zoom because of the solar eclipse. I'll be planning on traveling to see that, which that was something I figured out that I had to do about 7 years ago. Sorry for not informing you then. So anyway, but otherwise, I hope you don't really mind about that during doing class over Zoom. So with regards to the homeworks that we have left, we have recursion, index tree. So notice that we've got recursion's moderately big, and I plan on going over that in detail, in various ways today, taking questions on that. Index tree, with regards to that, we've got that one's fairly straightforward. The main thing that you're going to have is the kind of the mental hoop of having a data structure where the nodes store other data structures. So Cheater's Hangman is one of my favorites. And then the sorting algorithms, that will be, so our second exam will probably be next month, sometime between sometime around the Cheater's Hangman due date, either slightly before or after that. Okay, so that's when that will be, because the next exam focuses on primarily trees. Password cracking is going to be the last assignment, and I just simply set that to the last due date. Okay, so let's see, exam 1 corrections, open that up and modify. Okay, and let's go ahead and add that in. Redo, sorted, linked list questions for half of the points you lost. It will be put into this. So also we're not going to change your grade. So the way it's going to work is that your exam grade won't change. Instead, I've created a separate field for corrections. That way I can still, see what the average is on the exam. And that separate field is just like a out of 0, so that will be directly added to your score. Okay. So now with regards to the, so rather than going around today, I'm going to probably help you with the homework. So let's talk about recursion in general. So recursion, this window. So hopefully you've had the chance, since the original due date was today, to really kind of crunch on this and kind of look at these two things. So let's look at Queens and Sudoku. Okay. So the primary thing about the 8 Queens problem is that we have basically a couple of different methods here that you had to write. You have the public, static, Boolean solve, which is our primary recursive method, which takes in a board of some kind, as well as basically your position in the board. And what we said for the 8 queens problem is that we've got a chessboard and we're solving from left to right. We're figuring out in which for this column, which row do we put this queen in? Make sense for everybody? Okay. Now the thing about recursion is that it looks a lot easier than it actually is. Sorry, it looks a lot easier than you actually think it would be, and a lot of your first impressions when you're dealing with recursion is that works. It's that simple. That is the reaction for recursion, okay? Because it doesn't feel like it should work. It feels like magic. So by default, we're going to say it's not a safe place to put a queen, okay? By default, we say it's not a safe place to put a queen. And what we need to do is we basically need to come up with our base case. Now remember, basically the way recursion works is that we kind of set up a base case, and then we basically use once we establish a base case, we establish kind of a top-down problem-solving technique that makes progress to the base case. What do I mean by base case? I mean if it's fairly simple for us to figure out. When would we have a very simple thing to figure out? If the column is equal to board dot length, which is 8. In other words, if the column is out of bounds, meaning we've gone all the way, right? We're going to start at column 0, go to column 1, column 2, column 3, column 4, column 5. If we go all the way out of bounds, guess what? We're done, right? We're done. So in that case, we return true. That's what a base case is. Base cases should also always kind of be dirt simple. They should return true or 0 or 1 or some very basic answer. Like in the Fibonacci sequence, it will pretty much return 1 for our first things. Okay? Next is we ask, so if you look at the PDF, right, refer back to the PDF for this assignment. Okay? So let's go ahead and pull this up so that you have reference, because it's probably been a week since you looked at that, right? Yeah, no worries. Like I said, I expected you to do exactly the amount of work I did over break. So, and I had a very busy break with my kid. So the next one says, so basically, look at our solve function, board position. If the position is such that there's nothing left to solve, if column is equal to 8, return true. For every possible choice. What is the choice? A choice here in the 8 queens problem is where we put the queen on the board. So and I'll hit for I, for row is equal to 0, board dot length, right? So in other words, for the values 0 through 7, right? I'm not hard coding it in case you wanted to try it on a smaller board or not or whatnot, right? So if for int row is equal to 0, row is less than board dot length, row plus plus. And I'm going over the recursion here and showing you the answer for this one, for this part, because honestly, this is not the hard part. This is actually the easy part once you are comfortable doing it. But it's that weird, am I actually doing it right? This looks way too easy for it to be right. That's the big step for here. It's rather cold in here today. All right, so row is equal to 0, rows less than board dot length. So now what is the hard part? It's this function that we're going to leave blank for right now, which is if valid choice, right? If it's a valid choice. So I'll actually refer to this is safe, right? Is it safe to put the queen here? If is safe to put board, given this board, given the row, and given the column, if it's safe to put the queen there, we do so, right? So right now it's giving me an error, and I never want to have errors when I code, right? So what I need to do is I need to hit this light bulb, and I'm just going to create the isSafe method right over here. See? It just generated for me, and it needs to return a Boolean. So I'm going to make it return a Boolean immediately so I don't have any errors in my code. And I'm just going to simply, just so I can get the recursion working, I'm going to say, what's safe? Everything is safe. Return true. Don't think about it right now. Just simply make sure the recursion is working, right? If every safe is true, if every choice is true, then I'm just simply always going to say the first space that I put a queen in is a good safe space. So if it's safe to put a queen at that row and column position, what am I going to do? I'm going to say, I'm going to put a queen there, which I'll represent with a 1. Row, column, equals 1. Make sense? Not equals 1. If board, row, column is equal to, oh, made a mistake there, double array there. And now I need to fix that to be a double array. Okay. Yeah, like I said, I'm very tired. Okay. So put that queen there, and then here's the recursion. If solve board call plus 1 equals true. You don't actually have to put in the equals true. You can just simply leave it like that. If we can solve it, so if from this position, so what this says, if from this position we can solve the next, and there's 2 ways to look at this. If we can solve the next column from this position, or if we can solve the rest of the board from this position. Right? Recursion is kind of the ultimate form of laziness. It says, I have to make a local decision. Where in my column am I going to place my queen? I can't solve the entire puzzle, but I can try solving just my column. So I'm going to solve just my column, and I'm going to tell the next row to solve, the next column to solve the entire puzzle. That's what I'm going to do. And the next column goes, oh, that's too difficult. I'm just going to solve my column, and I'm going to tell the next column to solve the entire puzzle. Here I am anthropomorphizing columns, I guess. So anyway, so if we get a true back, that means we hit this terminating condition. We got to the end at some point, and so we put return true here. And what that does is that if we go out of bounds, that will return true, which will return true to this, which will return true to whatever. So if we hit out of bounds in column 8, that will return true to column 7, which will then return true to column 6, which will then return true to column 5, and so on and so forth. So if we can put the queen there, we do so. Otherwise, and this part is also important, if we can put the queen there, we do so, and if we can solve it, great. Otherwise, that led to a dead end, so we pick up the queen. Make sense? Put down the queen, we pick it up. And if we see that matches right over here, we don't need to use this line over here because we picked up our queen already. And if we got here, that meant that we tried all of the rows and none of them were safe. So let's go ahead and test this. PSVM to hit main. Board is, so int int board is equal to new 8, an 8x8 board. I'll call solve on board and start at column 0. And then what I'm going to do is I'm going to then do a for each int array row in board. So for every row in the board, I'm going to sout, and this is actually a little trick I've learned after teaching this class for a couple of years, which is I'm going to do arrays dot toString row, which will print out and this converts that single row into a nice string for me to print out. So I go ahead and hit run, and hopefully I didn't make too much of a mockery of myself with this. Always a possibility. And there we go. So we've got a 1 all across the top, which is actually good here. Why? Because we said, hey, we've got a 1, we get over here and we say, okay, if it is safe, and we're saying everything is safe, so we always check row 0 first. Then we go into column, then we go to column 1, row 0, column 2, row 0, and it's always safe. right? So now the only thing we have left to do is to solve is the isSafe function, right? Make sense to everybody? The recursion's working perfectly. So all we have to do here is this isSafe function. Now, queens can capture in all 8 directions, but we only have to check 3 directions. We have to check to the left of the queen, the upper left diagonal, and the lower left diagonal, because those are the positions to the left, because there's never going to be any queens in the same column, because that we're choosing what row in the column to put it in. And then there's never going to be any queens to the right, because we're going left to right. So I'm going to make that simple. I'm going to say return is row safe. Let's go ahead and I'm going to just simply copy this a couple times. Return is row safe and is upper safe and is lower safe for upper diagonal and lower diagonal. Make sense to everybody? So now what I'm going to do here, of course, is that I've got undeclared functions here, so I'm going to simply create all 3 of them, and then I'm going to say I'm going to assume that they return true for right now. Can I? Why can't you quickly fix it? It's a. Okay. Oh, because I've got an error in the code already. So return true for this one. Now this should be able to fix itself. Return true. Why return true? Because again, we just want our code to always be able to run. If you can't run it, you can't test it. And if you can't test it, you're essentially coding blind. Return true. There we go. So, in other words, we can check all 3 directions independently rather than doing one mega function. We can check all 3 of these independently. So the way you want to do this is that you want to radiate outwards from row column, right? You want to what do I mean by that? Well, I'll give you kind of the way to do this. So assume it's good. So return true is what we want here. And then if you see a queen in the same row, return false. So we do this by saying for int I is less than, I'll leave that blank for right now. Okay, I is less than something, I++. And what we're going to do is we're going to start at board row column. Okay. And actually, we should probably start at, yeah. And what we're going to do is we're going to say we're going to ask if board row column in some kind of modification and that question mark might be 0. Is equal to a queen. Here, I'll explain in just a second because typing and explain wouldn't do anybody good. All right, so this needs to be modified so you understand, and we'll do that last. But basically what we're going to do is we're going to modify the row and column of that offset here for all of these. Okay, so row. So we're trying to see if a queen is on the same row, which means that what's going to change is the column. So the row's never going to change. Okay? For column, and again, what this statement is saying, hey, is there a queen in this location? So column plus. So what we want to do is that if our queen, so if you look at my mouse, my queen's over here. I want to check this space over here, and then this space over here. So I want to go to the left. I want to check to the left. So that means that what I want to do is subtract I. So what I'm going to do is that so what do I mean? If I am at, not 1, I. If I am at, say, if I'm in column 7, I want to check the same row, but in column 4, the same row, but in column 3, the same row, but in column 2, and same row in column 1. Make sense? So the question then becomes, what should I put here? And the answer is, well, what I want to, actually the entire thing needs to be rewritten. It's actually a trick question. What we want to do is here's what we do. We want to make sure we don't go out of bounds, so we're going to be very simple about that. We're going to be very kind of brutal and direct about it. Column minus I is greater than or equal to 0. Make sense right over there? All we're doing is saying, we've got this counter, I don't care how big this gets, so long as column minus I isn't out of bounds. Completely different way of thinking about it, right? But it works. It works really well, and it's really easy to write. You're saying, okay, I've got this term here, and I don't want this term to go out of bounds. It's so much easier than trying to calculate it, okay, based on where you are. So if we run this now, it will go into an infinite. Nope, it won't go into an infinite loop because, again, we're increasing a negative over here. So now nothing's going to be in the same row, which is great. Now, believe it or not, we can use the same kind of configuration over here for the other two. We use the same problem-solving concept over here for the upper left and the lower left. You don't need two variables. You only need I. Okay? You only need I, and this is the part I'll leave to you. You only need I. Okay? And you just need to modify this to be, to fill in this part over there, fill in the Boolean, the check over there, and you need to fill in the appropriate, is it plus I or minus I, essentially. Now here's the trick, now here's the one hint for where students get stuck at. This is a Boolean statement. It's allowed to be a compound Boolean statement. You're allowed to throw an and in there. There you go. So, I've recorded this, so if you need me to check it back, so if you need to refer back to this later, I'll upload, it's going to be uploaded on YouTube so you can go through it. So that's that for right now. So with Sudoku, I'm going to also give you it's a very similar process for Sudoku, and I'm not going to do nearly as much for Sudoku. I will help with the base case, though. Okay? For Sudoku, it's a bit different. Why? Because you got two arguments, int row and int column. Your position is described by two things. You can take a single position and turn it into a row and column by doing math, by dividing and doing modular, but most people don't like that. It stinks. Okay? In which case over here, for this one, what are our base cases? Our base cases are a bit different. We're going to be going left to right across this. Your perspective. We're going left to right across the Sudoku board. Okay, and when we hit the end of a row, we go on to the next row. So if column equals board.length, in other words, if the column goes out of bounds, what we do is we say column is equal to 0. We reset to the beginning of the row, and we say row plus plus. We go to the next row. Make sense? So if our column goes out of bounds from left to right, we go on to the next row. Make sense? And then, likewise, if our row is out of bounds now, board.length, then if we're out of rows, then we're done with the puzzle, right? Return true. So those are that's our one base case. We also have one other base case, which is kind of weird. Or rather, one we actually have two recursive cases. One of which is, and I'll give you that bit, which is what if board, row, column is not equal to 0? So what if what is this? This is if the square, Sudoku puzzles come with some squares pre-filled. This is what if the square's already been filled, right? Okay. Then what if the square's already been filled? In which case we go on to the next square. Return, that's what most students, and if you get an error, a lot of times it's because you missed this. Row, column, sorry, no, it's not that. Return, solve, board, row, col plus 1. There's your base case. Okay. And then you do the, well, for every possible choice you could have in that position, okay, which I'll leave to you. It's not too hard to do if you follow the same kind of logic I used over there, where you say, okay, it's any choice is good for this square, and then you've got a puzzle filled with the pre-given numbers, and every empty square is now filled with 1s, and then you try to make sure, okay, nothing's in the same row, nothing's in the same column. Make sense? Okay, now the last thing I want to mention is that I do not want to see this. I do not want to see a for loop followed by a for loop followed by a for loop. Because that means you're searching for an empty square. You know where you are. It's row column. That's where you are. That's your position. Don't search for a position. You know where you are. That's the kind of point of recursion. So don't, okay. So there we go. And then, by default, again, we return false over here. Okay. Now, let's go ahead over here. And what do I need to do? I need to comment this out to make it compile because I care about this. Now, for the rest of the day, we're going to do a in-class exercise that counts as a quiz grade. Don't worry. It's not a pop quiz. You're going to get credit. Okay. It's an A for effort here today. Make sense? So today what we're going to talk about is we are going to go over, but I wanted to do that, but I honestly realized, wait a second, just because of the spring break, doing the homework on the recursion is a bit of a mess. So there you go. We're going to do the Towers in Class assignment. It counts as a quiz grade. Refer to the, did you do? Hey, very close today from last time I modified this. 311 lecture. Okay. So you'll turn in what you have today. Just follow along, because today is what we're going to talk about is one of the videos I put up on my YouTube channel, which you may not have seen, which is the Towers of Hanoi, which is one of my favorite kind of recursive puzzles here. So Towers of Hanoi is a mathematical puzzle. It's also got some names. The Tower of Benares, that's new. Tower of Brahma, or Lucas's Tower. Ooh, they've expanded the names sometimes. Anyway, this is the model set that you typically see. You might see a set of this in a museum or a puzzle. It looks kind of one of those kids' toys with like rings and stuff that, for toddlers. Now, the goal of the Towers of Hanoi is 3 rules, right? All right, towers, and let's see, do they have a link to one at the bottom where I can play it? They sometimes do that. References. External link. Let's see. Towers of Hanoi, play. Okay, sure. So there we go. Oh yeah. So the way Towers of Hanoi works is that we've got some number of disks. It doesn't really matter. And the goal is to move all the disks from the start stack to the other stack. And I do mean stack, as in like the data structure. You can think of them as that, as we'll see in a second. Because you think, okay, you just want to move them. You just kind of just, great, done, easy puzzle. But no, there's a rule which says you can only move one at a time. Which, okay, not too hard. You just kind of reverse it, pop it all out onto here, now it's reversed, and then pop it all out. So the third rule, that's the kicker, which is that you can't take, for any piece, right? You can't place a bigger piece on top of it. It just doesn't work. Make sense? That's the kicker. So you can only move one at a time, and I'm not going to do 6. That would take way too long to solve. And you can't put one piece on top of another. Now, actually, this is a fairly cool recursive puzzle, and once you know the idea here, it's not really that hard to do it at all. And there you go. 7 moves. 3 discs with 7 moves. Okay. 4 discs goes like this. I'll explain my thought process over here. You see, I've got 4 discs, and the issue is I need to move 4 discs over to here. Now, that means the first thing that means that I need this bottom disc to be on the bottom over here. So I have to move this bottom disc over here. But I can't do so because I've got 3 discs in the way over here. Make sense? So that means that I have to move these 3 discs, a tower of size 3, over to here, into this middle peg. Okay, if I want to do that, I got to move the bottom disc over here, which I can't do because I've got these 2 suckers in the way, which means I have to move these 2 suckers in a tower over here. So, which I can do like this. See how I've got a tower 2 out of the way now, which means I can move a tower 3. Now I got to move these 2 guys on top so I can put the guy over there. This guy. So take these over here, which means I have to do this and put that on over here. So now I need to put this over here, which means that, let's see, I need to move the disk to size 2 over there, which means, and now, and again, 15 moves there. Annoyingly, I know it's hard to see the move counter up there. Annoyingly, this takes, if there are n disks, this takes 2 to the n minus 1 moves at minimum, assuming you play it perfectly. Okay? It takes 2 to the n. So 15 over here, which means the next step would be 31 moves. Okay, let's go through that. To move a disk, to move a pile size 5 over to here, what I need to do is I've got to move the bottom over here, which means I have to move a pile of size 4 over to here, which means a pile of size 3 over to here, which means a pile of size 2, which means a size 1 over here. So 2 over here, which means size 3 over here. So I can move a stack of size 4 into the middle peg. So this 3 has to go over to here, which means the size 2 has to go over here, which means size 1 there, 2, 3, and see, 15 moves to move a pile of size 4. And then, boop. Okay, and now to move a pile of size 4 over here means I need to move a size 3 over here, a 2 over here, which means a 1 over here. Okay. And sometimes I just got to tell myself, trust the system. Just trust the system, you know. And now I just move a pile of size 3 over to here. Make sense? Okay, so to move a pile size 3 over here, I need to move a pile size 2 into the middle, which means move a pile size 1 over here, which feels so wrong to do, but you have to do it. So you can move it back over there. Pile size 2 means move this guy out of the way, move this on, and over here, come on, 31. Okay, so it takes twice as long each time. Okay, now why am I bringing this up? Well, you've heard me go through it. What I'm saying is that basically what I can do is that I thought of moving a size 5. The way I thought of that is that I needed to move a size 4 into the middle. To move a size 4 into the middle, I had to move the size 3 over here, which meant I moved the size 2, and then moving a 1 was trivial, right? And that's kind of the way it works for Towers of Hanoi. Okay? So, or if you need a visual representation, okay? If you need a visual representation, Wikipedia's got these great things, right? For size 4, we're moving everything over to here, which is split up into 3 steps. To move a size 4, You move size 3 out of the way to move the bottom disk over, right? To move another size 3 over there. So let's write down some pseudocode for this, okay? Okay, some pseudocode. Let's see. Let's see, do I have anything? Cool. Okay, so some pseudocode in here. So move n disks from source to destination using the auxiliary. Okay, so I'm moving n disks from a source peg to a destination, and then I have the third one as just like as an argument over there. Make sense? So the way it works is that I say if they're, well, it's just pretty straightforward over here. If n is greater than 0, right? If n is greater than 0, what do? I'm going to move n minus 1 disks out of the way from the source to not the destination, but to the auxiliary peg, right? Move them out of the way to the third peg. And the destination is just our third random peg, so I keep it over there, right? From the source to destination over there. Move, then I'll print status. I'll print out our 3 pegs, and I'll go into that in a second, okay? Just print our status update, basically to show that we've done that. Actually, let's not do that there. I'll do that later. What we'll do is that we will then, now that we've moved the 3 disks out of the way, we do source.pop, right? And then destination.push, right? Make sense? So I moved out everything out of the way. I moved n minus 1 disks out of the way. Then I just simply took this source one and put it onto our destination. So I moved that 1 disk. And then I had this giant pile that I just hand waved that I moved, right? So instead what I'm going to do is I'm going to take that giant pile of n minus 1 disks. They are currently in auxiliary, and I want to move them on top of everything else, which means I move it from the auxiliary to the destination, and that means the source is the one over there to use. And then what I'll do at that point is that I will print our status as a result. Okay. Now, obviously, this is magic and nowhere near a working code. This is just pseudocode, and you shouldn't really, and you should expect to do something a lot more complicated. It's one source. Append. Sep is equal to, sorry, I'm just switching. And then A is equal to, there you go, because the weight is equal to 3 to 1, B is equal to, C is equal to, and what should be, move 3, A, C, B. And now that should be a working Python program. So not much changed, in fact, at all. That's what I say when I said earlier about recursion feels like it shouldn't work, but it does. That's it in working Python. Now, a couple things to note over here, because you're going to be implementing this in Java. And then, well, I'll give you basically about 15 minutes to try implementing it in Java. And then, well, I'll come and show you I'll implement it in Java. Couple of points to note before you get started. Okay, the append is because Java doesn't have push. Sorry, Python doesn't have push. It has append. It just uses append and pop. Okay. Next is note that it says source destination auxiliary, but I print out ABC over here. The reason I put ABC over there is because those are global arguments, which means in Java they'd have to be static variables. The reason for this is because source destination auxiliary will always swap what they are based on what your function, where you are in the recursion, right? They always just change up, which is the source, which is the destination, which is the auxiliary. So we need a name from outside to keep them consistent with each other in order to print them in the same order. Make sense? So in Java, you'd have to have them as like, over here, static, stack, A, right? Make sense? And then you'd call them in main, and then you'd feed them in main. But you'd have them, but by making them static, you'd essentially make them global variables for everything. All right? So I'll give you about 15 minutes to try that, and then get as far as you can. If you can't, I'll show you the answer. Okay? Okay, so all right, so let's go ahead and get this going. So overall, it's not going to be too different. Again, part of this is to just get your brain kind of back into gear after taking a week of not programming. It's not that I know what you did over the break. I just know what you didn't do over the break. All right, so let's go ahead and first off, I'm going to do that. I'm going to create those. Rather than doing this at the bottom, I'm going to do this at the top, right over here. Static stack A is equal to, actually, let's import this first. And let's see, can I use it? Can I use a linked list? New linked. Can I do this? Am I allowed to? No, stack cannot fit in linked list, or you can't implement it of that type. Okay, in that case, can I just do a new stack? Can I? Yes, I can. Stack's not an interface. Great. Okay, I sometimes forget what's an interface and not, so let's go ahead and copy these suckers so that we get A, B, and C. Then what we'll do is that we do PSV in our main method at the bottom. I will just simply say, hey, A.push. We are going to push down the bottom. A.push. 2. And again, the reason that I have to do it this weird way, honestly, you rarely have to do this recursion, but the reason we're doing this is because we need all this outside. Oh, let's go ahead and get rid of that warning. We need this. We need to be able to reference them in the ABC order. That's the point. The reason we do this is that we can reference all stacks in the ABC order rather than whatever order they are in the move function. So then we'll call move, which we haven't written yet, but that's not a problem. Move 3 to from A to C, using B. Very often that you say A to B using C, but it would still work. It'd just be everything would end up in the middle instead. Okay, and now we just simply say, hey, Java, can you create this function with all the arguments, please? And it does. So I'm going to move this up here because I like to have my main at the bottom. Give it, and we'll go ahead and give it the names. Stack source. Let's see. Does this help? Okay. Wow, that's loud today. All right. So source. There we go. Source. This last one over here should be aux, and then destination. And now the main question for me is actually where to print these, but that's fine. So if n is greater than 0, then we can, the reason we do this is that if it's equal to 0, then we don't move anything. So move n minus 1 disks from source to destination. So, yeah, from source to destination using auxiliary. No, actually, we have to move them out of the way. So it's source to auxiliary using destination. So we move them. We move those 3 disks out. We move the n minus 1 disks out of the way. And then what we'll do is that we will then do we move source dot pop, and then dest dot push. So we move everything out of the way so that we can move the bottom disk to the destination, and then we move all the disks that we moved out of the way from auxiliary to source using destination over there. Okay. Let's see. Auxiliary, not auxiliary to source. Auxiliary to destination. I'm tired. Sorry. Source. All right, and now we need to. I just need to figure out where I'm printing them, which is the best place to put them, and I think it's Sout A, Sout B, because I can't do it fancy like I can in Python. Okay, and let's make it a bit easier to read with a blank printout to separate them, or even better, we can just do that. All right, so let's see. Says move 3 to 1. Okay, so it's not doing them in the right order because I did not put that this statement. Where does this need to go? Probably before I move everything. Yeah, let's go ahead and print out everything before I move everything. So we'll see how that goes. No. Or in that case, right after I move that middle disk. That makes sense. Yeah, that's what we need to do. So, and the difference between, now that was inadvertently a great preview of pre-order, post-order, and in order, which you probably tackled in 1051, or sorry, not 1051, but 1166 or 2166. So 3 to 2. So our first move is to move 1 out of the way over here, so we can move the 2 over here, so you can put the 1 over here, right? Then we move the 3 over to there, so that we can move the 1 out of the way, 2 over there. So let's go ahead and now let's go ahead and make this a bit more variable, shall we? By just simply saying n is equal to 5, or sorry, we'll say int n is equal to some number, right? And then what we'll do is we'll say for int I equals 5, sorry, int I is equal to n, I is greater than or equal to 1, I minus minus, a dot push ion. And now we can just, and then we replace it with n over here. And now we can do and now we can print out all 32 moves for, that we need to do this. Which is great. So there you go. There is our move function. Let's see. You know, give me 1 second. I can easily just simply drop this on Discord, which I'm going to do. I mean, and if you don't have it, you can, Discord, you can always just simply refer back to this lecture. And the fun thing about Discord is I can, the fun thing about Discord is that if you check, I know how to format it. I know how to format it so that it looks like actual code. So there you go. I've dropped it on Discord. If you need it, it's right here too. So what you'll want to do with this is take what you got, take what we got, or take what you wrote if you managed to write it, and just simply upload it here. Even if it's my code, you can upload it. I just wanted to show, basically this is a, did you participate and try this and try to get your brain working in gear because it's been a long break. Okay. Now, okay.